watch that. Anthony's mom yelling at his phone to it.
That looks pretty good. I don't know. Okay. All right, let me tell you about this new chapter. Everything we do from now on is going to be hit and miss from now on. We built up to, and it was a great time to have the midterm. And by the way, midterm grades were better than I expected. Like, I'll give you the actual stats on it when I give you back your grades at the end of the period. But they were out of 150 points total. So your numbers, like, if I tell you got 130, doesn't mean you got 30 bonus points. But the grades were really very good. And considering all the stuff that was on this is very comprehensive. There was almost nothing from the first half of the year that wasn't on there, at least in some way, shape, or form. I was happy with that. But from now on, it's all different. We're going to be hitting and miss different topics. So the first topic we're going to talk about today and in the next chapter, these first two chapters after stoichiometry, are gases. We have a whole chapter on gases now and have a test on it. Then we have another chapter on gases that's going to talk about a different aspect of them. Then we'll have a chapter on solids and liquids. Then we'll have a chapter on solutions, putting them all together. Then we'll talk about acids and bases, nuclear chemistry, and a couple of other things along the way. But there's no longer, the good news about this is, if you were having trouble because you were not liking the fact that it was all building on itself, well, this chapter, I could have taught you this chapter pretty much in September. Okay, there's a couple of little things you need to know, but not much. For example, you're not going to use the periodic table in this chapter at all. You're not going to write compounds or formulas. You're not going to do stoichiometry. You're not going to balance equations. You're not going to do any of that stuff. And that was, all of that led up to that. This is going to be pretty much a self-contained chapter. Now, the next chapter, we will be putting gases with some stuff we'd already covered. All right, but that's how it's going to be from now on. And I think that's a good and a bad thing. I mean, the bad part about things building on themselves is that, of course, if you were absent a lot in chapter 3 and you never got this down really well, it didn't go away. It kept coming back up. The bad part, that's the bad part. The good part is, if you're kind of following along here, the midterm turned out to be pretty easy because you were using all that stuff anyway. I mean, to do stoichiometry, you had to be able to write an equation. To write an equation, you had to be able to write formulas. To write formulas, you had to be able to use the periodic table and get the charges and all that stuff. So it wasn't like you really had to study a lot for that midterm. And still, I bet you most people didn't study a lot for that midterm, and yet your grades are pretty good. I'll give those to you at the end of the period. All right, let's start this new chapter. It's on gases, and that's what I want to talk about first. And actually, before I get to the actual notes, I want to talk about something called the kinetic theory. And I'll show you a little animation here I have, which is kind of cool. The kinetic theory explains what's going on, not just in gases, but in all phases of matter. So let me show you something here. Turn that light off for me. All right, check this out. I have a little animation. It's going to illustrate what's going on. There are 5 points to 5 statements to the kinetic theory, and I'm going to illustrate all 5 of them right here. So keep these in your head. And I'll show you this again throughout this chapter. Probably throughout this week, we're going to refer back to this. Let me put some air into here. Here's an empty chamber. I got nothing there. So I'll pump this guy up, and I'll put some molecules in there. Now this, like you guys, all the internet games you have now, they all use real physics. Most of the games where you're on a little skateboard or a little car or whatever, it has gravity, and that's what all these little animations pretty much can illustrate those laws of physics. If you're watching these guys, this is what's going on in a gas. You just can't see it. The molecules are too small to see. But this is what the molecules of a gas are doing. They're bouncing into each other, and you can see that this is happening, to these actual little molecules. They're bouncing into each other, and if somebody hits the right way, they go off at different angles. Sometimes they go a little faster, sometimes a little slower, but they're not really slowing down as a whole. Okay, this illustrates all the points I'm about to put on the board for you. First of all, the first statement is all gases, all solids, all liquids for that matter, are made of small particles called atoms or molecules. We've heard that before. Secondly, they're moving. They're moving all the time. They're moving randomly. Okay? All right? Third, if I can illustrate with this, watch what happens. Let me say I heat this guy up. I put a little fire under him. What's going to happen to those molecules? What are they doing now? Yeah, they're moving faster. Okay? They're moving a lot faster. Okay? I mean, temperature higher, pressure's going up. We're going to talk about pressure and volume and temperature, how they're all related to these guys together. Okay? Let me cool them down. I'll put a little ice underneath. That's ice. It's supposed to be ice at that point. Cool them back down a little bit. So, all right. So that's the third thing. If you heat them up, depending on how fast they move, they have more energy. That's all related. There are two special things about gases that are also going to be related on those, but I can't come back to this. That's why I'm showing it to you now while I'm giving you the actual PowerPoint. All right. So there are two things that are special about gases. When these guys bang into each other, they're not losing energy. Okay, they're not slowing down. Okay, they undergo what's called elastic collisions. And secondly, they're not sticking together either. When they bang into each other, they're not actually sticking. So those are the two. Now that's not the case for solids and liquids. That's just for gases. So let's illustrate. This thing illustrates all of those points. And by the way, just a hint ahead now to the next couple of days we're going to be talking. What's going to happen if I change the volume of this container? If I were to pull back on it, what does it do? Notice the gas expanded into this area, didn't it? Right? It filled up that area, and the pressure went down a little bit, I guess. If I push it together, notice the pressure going up. See that? Right? Because I pushed them all, made them closer together. Okay. And the temperature also went up. The relationship between volume, temperature, right here, and pressure is something we're going to talk about all week, all chapter. And that's what this whole chapter is about, the relationship between volume, temperature, and pressure in a gas. And that's why it has almost nothing to do with stuff we've already covered. There's no chemical reactions involved in this. We're just looking at gases and how they're related. All right, keep all that in mind while I start giving you notes. You can put that backlight back on. All right. First, the kinetic theory. Physical characteristics of gases. The kinetic theory describes the physical characteristics of gases. What I give you in this chapter, like I said, is pretty much, not entirely self-contained. So if you're paying attention to this, and I hope you are, you have to keep a couple things in mind. This isn't going to be like the last test you just took on stoichiometry. Most of you guys, you're in the honors class because you're pretty smart anyway. You didn't have to do a whole lot of studying for the stoichiometry test or the test that was before that, which was the test on reactions. My guess is most of you did no studying for that and still got A's on the test. Very easy to do. Why? Because it had built to that point and you knew it. That is not the case for this test. This is the bad side of that, being a self-contained chapter. All your prior work, all your A's from the previous, your 95s and 99s or 101s from the previous two marking periods mean nothing for this chapter. You're going to have to actually study for this test. And the material in here is not going to be all problems like it was for stoichiometry. You remember the stoichiometry test? It was one side, all problems. This test will be a mix. It will have questions and it will have problems. It will have both. So the stuff that you'll do badly on will be the stuff on the questions. Like, for example, the 5 points of the kinetic theory. First one, as I just said, all matter consists of very small particles. You're going to have to know these. Those particles are called atoms or molecules, and we know that. We kind of know that from our first chapter on atoms, which is chapter 3. We kind of know it from that. And so that's not a big surprise to anybody. Everybody kind of knows that one. The second one, and I don't think anybody's really surprised by this, especially when you think back to that little animation I just showed you, and you're going to see again, these particles are moving around. They're in constant motion. It's not so hard to think of that. I think we kind of know gases do that. I'm going to illustrate a lot of this stuff for you with some demonstrations throughout this chapter. I've got 3 today. I've probably got 3 tomorrow, and maybe even 1 or 2 the next day. So this whole week, we're going to have quite a few demos to illustrate all of these points. Some of them are pretty cool, especially when you deal with gases. There's some pretty neat stuff you can talk about and do. There's no big surprise there. They're in constant motion. And the last one, no big surprise. If I heat them up, they move faster. The average kinetic energy of the molecules is proportional to the temperature. That's just a fancy way of saying, hotter gases are going to be moving more and have more energy. Colder ones are going to be moving less. Now, those 3 things, I don't think anybody, again, would be surprised to see are applied to everything. Solids, liquids, and gases. Okay? These next 2 I'm going to put down here only apply to gases. And you're going to want to write that down next to these next 2. All right, when you're all done, after you've written them. These next two only apply to gases. Solids and liquids, these are not the case for. As you saw, as I illustrated a minute ago with those moving molecules, they bang into each other, and then they keep going. You guys are in physics, right? Are you guys doing anything with vectors yet? Or like Mr. Schrader talking about how, maybe on a pool table, a ball hits another ball at a certain momentum, a certain mass of the ball, the speed of the ball, right? Okay. Well, you all know that that's not a perfectly elastic collision, right? He tells you that. You have to assume it is to figure out what angle they're going to go off at, and what speed, and how far, whatever. But they're going to stop moving eventually, even on a pool table, even on a hockey table. You know those air hockey tables, which is what you usually want to use. This is better because that puck will go back and forth maybe 5-6 times, but eventually it slows down and it's done. It doesn't move anymore. That's not the case for gases. And what we call an ideal gas, the particles undergo purely elastic collisions, and they don't lose energy in those collisions. Okay? This is an ideal gas. So it's not like on a hockey table or a pool table where the ball just stops moving eventually. These molecules are moving. These atoms are moving. They bang into each other, and they don't lose energy. But something else you notice about those guys too, they banged into each other and they didn't stick either. They bounced off of each other, right? So basically, these guys have no real forces of attraction. Now, by the way, that's not really true. There are some forces of attraction between them, all right? But we have to assume that in all of our calculations that they're really not being attracted to each other in any way in the gaseous phase. In reality, there's going to be some attraction. But to do our calculations, we're going to assume not. So those are the 5 statements of the kinetic theory. And you're going to have to know them all. These last two, I definitely want to make sure you highlight. Because these two, okay, put a little star by those. Those last two are only for gases. Okay, only gases. The first 3 apply to everything. Absolutely everything. Solids, liquids, and gas. All solids and liquids are made of molecules and atoms. They're in constant motion. Doesn't look like it, but they are. And if I heat them up, they move faster. And if I cool them down, they move slower. Okay? It's these two that I can't say that about. All right. So there's the kinetic theory. And again, you're going to see a section in the test on this. By the way, the total amount of notes you're going to see on the test, today chapter always starts off with more notes, then we get to more of the problems. Maybe 20% of this test is going to be question-oriented, maybe 25 at the most. I'll tell you more when I get to the test. The majority of this test is problems. And when we get to those problems, you'll see what I mean. Okay, we're going to get to them probably starting tomorrow, not today. Today you're getting mostly the notes. All right. Let's talk about the properties of gas. This is where I have quite a few demos to show you on this. Okay? You're also going to see something else about when I talk about solids, liquids, and gases. As I talk about each of them, I'm going to talk about how the kinetic theory applies to them and how it affects their properties. Okay? The first property, you probably remember memorizing in elementary school or middle school. Gases have no definite what? No definite what? Shape or volume. Shape or volume. No definite shape and no definite volume. Before I'm going to hint ahead, that's called expansion. They have no definite shape or volume. I'm going to hint ahead on that one to liquids and solids. See if you can figure those out as well. You probably all remember memorizing that. And it was illustrated perhaps for you, but I'm going to illustrate these things as well. When I pulled back on that box and all the molecules, because they were moving anyway, ended up moving into that area, that's expansion. Okay? They fill up the shape of whatever container I put them in. Okay? And they fill up the volume. If I open a bottle of perfume that's going to evaporate, those fumes that are evaporating are going to try to fill the room. Okay? They won't, but it won't completely fill the room probably, but if I will probably be able to smell that perfume if I open it up, or if I spilled it on the floor. Like a lot of times you're walking down the hallway, somebody, spilled a bottle of body spray in their locker. You know where it was because it tries to fill the whole room. Okay? It has no definite shape. It has no definite volume. Let's talk about, again, hinting ahead. What can I say about a liquid? Does a liquid have a definite volume? Can I measure the volume of a liquid? Yeah. And it doesn't change. If I put my water from a big glass into a small glass, it's the same amount of water, which is funny because it's one of those things, by the way, I remember from my psych class, I don't know why, from college, but one of the things I remember about that was at certain stages, a child can watch you do that. Watch you take water and pour the same amount of water into a small glass and into a tall glass. You can watch you do it. And then you ask them, which one has more water? And they'll say the tall glass does. Now, you guys know, if you watch me pour the water into here and then pour it into another glass, it's the same amount of water. But the child doesn't understand that. I don't know what age that is, 2 years old, whatever. But that actually does happen. It's one of those things that stuck with me for some reason. Anyway, so a liquid has a definite volume, but does it have a definite shape? No, I can have a tall glass, short glass, round glass, square glass, doesn't matter. All right, last one, solid. What does solid have? Does it have a definite volume?
Yep.
Yeah. Does it have a definite shape?
Yep.
Yeah. So solids, these two things, pretty much, depending on what you're talking about, you should be able to get those right. And I think you would because, like I said, you've been getting that since you were in elementary school. Now, this next one, I have a little demo for you. Okay? And it is fluidity. A gas is considered a fluid. It's considered a fluid because the particles slide past each other easily. And I'm going to illustrate that for you with a little demonstration. Okay? You copy that down and then look up here. Now I'm going to hopefully not burn myself. I'm going to put that in there. Good, I didn't. I got a little candle in there, like a candle in the wind. So I make sure people watching at home can see it. And I'm going to take some baking soda. And I'm going to add some vinegar to it. Now, watch this. Add the vinegar to the baking soda. We all see it fizzing. Okay, we all hear it fizzing. And it's making a gas. The thing about this gas is, watch what I can do with it. Ta-da! What'd I do? I just poured it. Because the gas that it made, do you know what gas it made? Carbon dioxide. It's heavier than air. So I could actually pour it. You couldn't see it. All right, you couldn't see it being poured, but it was poured in there. The liquid's still down here, and you had to put it out because carbon dioxide will put out the flame. All right, don't tell Al Gore again. We're making CO2, global warming. All right, so gases are fluids. All right, the particles slide past each other. I can pour it. All right, and that's what makes something a fluid. Liquids are also fluids. Solids obviously are not. All right, let me move this guy out of the way. That's a pretty easy demo. I got a couple better ones coming up here pretty soon. Well, one better one coming up. And tomorrow I got some neat ones. Low density. Gases have a very low density compared to their solid or liquid phase. And it's a huge difference between it. The difference between a solid and a liquid is not much at all. And it's not probably what you think, even the direction, because you're so used to dealing with water. But gases are a lot less dense than either the liquid or the solid phase of the same substance. All right? About 1,000 times less dense. Now, if you think about it, I want to ask you a question, see if you get it right. Which is more dense? In most cases, which is more dense, the solid or the liquid phase of a substance? Which is more dense? Katie. She says the liquid's more dense. And she probably says that because most of the time, what's the one liquid you're most familiar with it's also in the form of a solid? Water. And we know that ice floats. But remember the video I showed you about water a long time ago? We're talking about intermolecular forces, hydrogen bonding. Water is completely unusual. He's a rebel. He doesn't. Most things don't do that. The vast majority of things, solid phase is a little bit denser than their liquid phase. When I say a little bit denser, I mean only a little bit. Certainly not 1,000 times. The gas, here's what I'm saying. If I were to take a milliliter of water and boil it, it would fill up a liter, like this much. So a milliliter, which is like, half of an eyedropper, boiled to a vapor would fill up a liter. It's about 1,000 times less dense. Okay, it's a big difference between a liquid and a gas. The difference between a solid and a liquid is very small. Okay. All right, so that's low density. Next one I have a little demonstration for, and that's on compressibility. It's a pretty easy demonstration. We're going to see these things in the future. We're going to do a lab with them. Syringes. The main reason we have a chapter that's going to be longer than 2 days is this property right here. Because if it wasn't for this property, we'd be done with this chapter in about 2 days. But here's the difference. Here's the problem. It's not enough for me to tell you that I have, in this case, 115 milliliters of a gas. It means absolutely nothing if I say that. You know why? Because it depends on the pressure. If I push down on this gas, okay, what's happening? That volume's now half of what it was. Okay, or even more, even less than half. You know what else would matter? If I put this into, and we're going to do all of these things, you put these into cold water. What's going to happen to this thing? It's going to shrink. If I put it into hot boiling water, what's it going to do? It's going to expand. Gases change their volume. Liquids don't. I mean, they do a little bit, but it's negligible. Solids don't. Okay, they're negligible. I mean, it is true. A liquid will expand a little bit if it gets cold. I mean, if it gets hot. But for the most part, they don't do it like gases do. Gases, we have a whole lab on this. We have a couple of labs on this. Well, we're going to calculate, we're going to determine the relationship between pressure and volume. Okay, you're going to see that relationship. And it turns out to be a pretty easy relationship. You know what happens if I double the pressure? I have the volume. Yeah. And if I decrease the pressure, by that factor, whatever factor it is, I increase the volume by that factor. Same thing's true with temperature. Pretty much the same basic idea. We're going to call these guys Boyle's Law, Charles' Law, Charbel Law. Charbel. Okay. No. Yeah. Anyway, we'll call these different names. The combined gas law, and that's what's going to take us so much time. All right, so compressibility is the reason this chapter is so long. We have to be able to calculate the volume only if we know the pressure and the temperature as well. You don't even know how to measure temperature. You don't know what we're going to do to measure temperature. So I'm going to have to talk about all of that. All right. The last one that I have a demonstration for is, well, you know what? Instead of giving it to you, let me see if you can figure out what it is. Check this guy out. All right. Put him on here. Make sure you can see him. And get rid of that. So I'll make sure you can see it at home too. People who aren't here. Now, you see how labeled? I don't know if you can see those labels on there. But on this side, I'm going to put a cotton ball soaked with concentrated hydrochloric acid. On this side, I'm going to put a cotton ball soaked with concentrated ammonia. You're not used to dealing with either of those guys, even in this lab. You say, well, we use ammonia at home all the time. No, you don't. The ammonia you use at home is like 5% ammonia. The stuff I'm going to use is like 95% ammonia. Okay? The stuff over here, hydrochloric acid, in the back of the lab, first of all, you don't use hydrochloric acid at home anyway. But if you were to use it in the back of the lab, I usually use about 1 molar. That means 1 mole of the hydrochloric acid is actually in every liter. What I'm going to use over there is like, I think it's 12 molar. So it's like way stronger. And you don't want to spill the 1 molar on yourself. You certainly wouldn't want to spill those. Matter of fact, the reason I have both of those in the fume hood over there is that if I were to open the lids of either of them, they will fume. They will give off fumes, and you'll see them when I do that in the fume hood. But I need Haley to move for a little bit. You can just move over to that table. It's free anyway. And I'm going to get these for you and show you this little demonstration. Because I don't want Haley to get burned. Burn! Alright. Can I put my gloves? I look like the guy from Breaking Bad with these gloves.
You teach us how to make that.
Yeah. That's too late. Everybody knows the program anyway. Alright. Put my fuel on over here. Alright. Hydrochloric acid in. Whoa, check this out. I'm just going to open the bottles next to each other. Y'all look at this instead of your phone, Katie. Just letting them sit next to each other. Check it out. See that? See those fumes? Everybody see them? Okay. All right. Now I'm going to soak a cotton swab in each of these. And they smell. I mean, right up your nose. Anthony knows how hydrochloric acid will go right up your nose. Exactly. So I'm going to keep that in there. I'm going to wash my hand off. And I'm going to dry it off actually too. Because ammonia is very soluble in water. I really don't want my hands to be wet. It's not going to hurt me, but it's going to, that ammonia will dissolve in the water very quickly. And I want it to be strong enough to do what I want it to do. Close enough. Then on that one. Get this guy up. Knock him out. Put him in there. All right. Now, I'm going to bring these guys over here. The hydrochloric acid is in my right hand, and the ammonia is in my left. That's okay. It's in the fume hood. I'm going to take these guys. I'm going to put them into there at the same time. Okay. Oh, no, stop. Open that window for me over there, Haley. And the other window, too. Both of those.
Oh, I see it.
Now, okay, check this out. If you look in the middle, keep your eyes in the middle. There's no air in here now. There's no air. There's no wind blowing this either direction because they're both clogged on both sides. So what you're looking for in here, and could you hit that light for me so they might be able to see it?
Oh, there it is.
Oh, there it is. On, both of them on. Okay, see that? There he is, formed right there. Okay? All right. What property is that I'm going to write on the board in a second? No wind blowing these. They simply moved all by themselves from a high to a low concentration. What do we call that in biology? Diffusion, exactly. All right, so let's write that down. Diffusion. I know it's cold, but I'm going to put these back away so I can.
Best part right there.
Okay. That's why we got the windows open. Oh, and that's also why, by the way, you should never mix different kinds of cleaners.
Why?
All right, because you will actually can be overcome by the fumes of certain cleaners are acidic acid based. Other ones are basic. Some have ammonia. You know that. A good example of an ammonia cleaner would be Windex. Other ones that are also basic would be like bleach. But there are also cleaners that are acidic. And if you put these two guys together, they react and form what you just saw there, a cloud of that's you don't want to be inhaling. And certainly not in large amounts. People have been killed cleaning their tubs. It's overcome by the fumes. I believe it or not, it has happened. It can happen because you're not realizing it, and it's in a very enclosed space, and that can actually happen. Has happened. All right, good enough. Let me get this out of the way so I guess people at home can at least read the notes there. Put this over here. All right. So, where did we see diffusion in the past in biology? Remember? What do they have to do with? With water and the cell and...
I was going to say that.
Yeah, and what else? What's that other word that involves diffusion? Osmosis, right. Remember osmosis?
Osmosis Jones.
Osmosis Jones. There you go. All right. By the way, osmosis does not work for studying. You can't just put, it doesn't work, okay? Nothing gets in there. But osmosis was movement of water across a semi-permeable membrane. Remember that? Because it had it lets water across, but not sugar or salt or whatever it was that was in there, and that's why the cell will shrink or expand, and you had to be able to predict the hypertonic, hypotonic. Remember all those terms from bio? Good. You should. You guys all passed your bio keystone, so you certainly should. All right, good enough.